This video will focus on the different definitions that we have for acids and bases. And then within one of the definitions, we'll actually talk about conjugate base and acid pairs. So you need to be able to determine what those conjugate pairs would be and the relative strength and weakness of the pair. So the first video focused on talking about acids and bases as a concept and giving some general characteristics of them. Now we get into the chemistry. Okay? So there are three different theories behind what an acid and a base is in terms of what the chemical structure is. Okay, and we're going to go through all three theories. Only two of them we really need information on, but I want you to be aware of all three. So really, when you think about an acid and a base, what is it? The first definition is Arrhenius's definition, and his definition of an acid is that it's a compound that contains a hydrogen, so that when it ionizes, you get hydrogen in solution. Okay? So examples of those are the ones listed and ones you've seen: hydrochloric acid, sulfuric acid, phosphoric acid. Okay? In each of those cases, when you look at the chemical formulas, they have hydrogen in the formula, which is allowed to come off when it dissociates in water. Three new terms, though, that come up with this first definition is monoprotic, diprotic, and triprotic. What protic level is a measure of how much hydrogen can come off per compound. Hydrochloric acid is monoprotic because if you look at it, there's just one mono hydrogen available to dissociate. Sulfuric acid, on the other hand, is diprotic because you have two hydrogens available to dissociate. So when you put that into solution, you would have two potential hydrogens available from one compound to basically become acid in solution. Triprotic then, phosphoric acid, where you have three hydrogens available to do the dissociating. So what this does in the end, it affects our math in that if we know how much of the compound is put in, you potentially have double or triple as much hydrogen produced. And it's the hydrogen that's measured in relation to being acidic or not. Okay, so an acid is a compound that contains a hydrogen that when put in solution will dissociate, and that's where you get the acid from. Bases in his definition then are just compounds that have hydroxide, so that when they dissociate, you'll increase the hydroxide concentration in your solution. Okay, that's Arrhenius's definition. So acids have hydrogen, bases have hydroxide. There was a problem with Arrhenius's definition, and the only problem comes in, well, predominantly with bases. Okay? Not every base does have a hydroxide. There are times with the compound structure allows you still to make a solution basic without it having OH available to donate into solution. So Bronsted-Lowry took this initial concept of hydrogen donor and OH donor and took it one step further to account for a greater variety of bases. Okay? Acids, instead of just being compounds with hydrogens that can dissociate, are called hydrogen ion donors. Okay? They have hydrogen available to give. So if you think about this, this is basically the same definition, right? Hydrogen available to give, hydrogen available to give. Oftentimes it's called a proton donor instead, because if you look at it, once it dissociates, it's H+. Once hydrogen loses its electron, all it has in a nucleus is a proton. So it's actually simply a proton moving when you dissociate a hydrogen. Bases have a much different definition here. Instead of it being a compound with a hydroxide available to dissociate into, bases are considered hydrogen ion acceptors. They take on the hydrogen. Okay. So if we look at the two chemical reactions below and look at from start to finish, when you put HCl, which is the second reaction, into water, you see that H2O is becoming H3O+. So basically that HCl, that acid, is donating its hydrogen to the water. So you can see where the hydrogen donation is happening. The first example then, if you look at the NH3 into water, your NH3 becomes NH4 and your water becomes OH-. So that NH3, which would be considered your base then, is a hydrogen ion acceptor. It accepted a hydrogen, which makes it a base. And you can see how here Arrhenius's idea of a base increasing the concentration of hydroxide still exists, right? This NH3 compound was able to increase the concentration of OH minus by essentially taking a hydrogen away from water. But NH3 is not a classic Arrhenius base because it has no OH actually in the compound. This change is not made by a dissociation of the NH3. Okay, so that's the main difference between Bronsted-Lowry and Arrhenius. The huge thing that comes